right, let's look at an example to see how these things get put together. All right, so let's say we have an equilibrium, we have the same equilibrium equation as we did in the previous video, right? Two BRCLs turning into BR2 and Cl2. And in addition to that, I tell you that the equilibrium constant of that reaction is 1.09 times 10 to the second. If I give you the following um, derived equation, right? So this is, you have the same reactants or you have the same species present in the equation for which you have the equilibrium constant value given, but a few things have been changed. So we're going to try to apply a Hess's law cycle to derive the equation that we have right here in order to find out what the equilibrium constant value is going to be. So first things first, if you look at the expression, you have the concentration of BRCl raised to the third power based on the second equation, all divided by the concentration of Br2 to the 3/2 power times the concentration of Cl2 raised to the 3/2 power. That's the new equilibrium expression. So if you look carefully, you're going to realize that, okay, first of all, BRCl is a product as opposed to being a reactant. So it looks like you took the inverse of the original reaction to swap the order of reactants and products. The other thing too is that instead of having one BR2, you have now 3/2. So in essence, it looks like you multiply the entire equation by 3/2. So notice what happens here for the expression. Technically speaking, you are taking the original equilibrium expression and raising it to the negative 3/2 power to end up with the equilibrium expression that you have down here. So what that tells you is that you simply need to take the value of the equilibrium constant 1.09 times 10 to the negative 2 and raise it to the negative 3/2 power. And that will give you the new value for the equilibrium constant, which in this case is 877. And because the value is greater than 1, this tells you that this reaction is going to go forward and it's going to be product favored to a high extent. All right, now let's take a look a little bit closer to gases. What happens when you have gases in the equation? As I told you before, you can actually input gases into the equilibrium expression. But if everything that you have in your reaction happens to be gases, there's a specific way in which you can refer to the reaction in terms of the equilibrium constant. And what I'm showing right here is basically a model, research lab, that is set up to handle gases. Here you have a dual manifold. A part of this manifold connects to a gas line, as you can see right here, and the other half actually connects to a vacuum pump, which is meant to evacuate your vessels so that you remove whatever air you have in there, and then you can actually input the gas that you're using into your vessel, so you can actually just add and remove reactants at will. And most of the gases that we deal with happen to be colorless. Some of them have some smell to it, other ones do not. A few of them actually have color, like bromine gas is pretty much red in color. Iodine gas is purple in color. Other gases are, kind of colorless. But you have specific glassware to, use them. But anyway, the main point here is that if your reaction contains only gases, then you can relate to the equilibrium expression in terms of pressure as opposed to concentration. And if that's the case, if you have only gases here, so you can input this as the pressure, the partial pressure of C raised to its balancing coefficient times the partial pressure of D raised to its balancing coefficient, all divided by the partial pressure of A raised to its balancing coefficient times the partial pressure of B raised to its balancing coefficient. And if you input the information that way, you're dealing with not the Kc, but rather the Kp, where the P stands for pressure. So, two different ways to express the equilibrium constant, but as it turns out, there's a way to actually correlate one with the other. And it comes in the form of the ideal gas law. So you may remember from your previous chemistry course or courses that PV equals nRT. This is the ideal gas law. And moreover, if you concentrate on the volume and the moles, you can actually derive the concentration. Specifically, divide both sides by the volume, and you're going to end up with moles over volume, which is the expression for molarity, the concentration of a substance. Also, divide both sides by RT, so you have P over RT equaling the concentration. This is now the expression that you can use to derive the identity of the Kp constant based from the Kc constant. So check this out. Another way to look at it too is that if you solve for the partial pressure, ultimately what you're doing is multiplying the molarity by RT. Alright, so check this out. When I take this equilibrium constant for the partial pressures, right? We have partial pressure of C, partial pressure of D, partial pressure of A, partial pressure of B. I'm going to literally input this expression for the partial pressure. Whatever I see P, I'm going to input concentration in molarity terms times RT. So what that means is that the partial pressure of C is now going to be concentration of C times RT all raised to the power of C. Partial pressure of D is going to be concentration of D times RT to the power of D. Partial pressure of A will be concentration of A times RT raised to the value of A. And partial pressure of B will be concentration of B times RT raised to the power of B. And what you can see right here is that in every single term you have RT, 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 RT. So you could actually factor out the RT terms, and what you're going to end up with is the typical concentration expression for the equilibrium constant, concentration of C to its coefficient times the concentration of D to its coefficient divided by the concentration of A to its coefficient times the concentration of B to its coefficient. So technically speaking, what you have here on the left side of this expression is the Kc equilibrium constant expression. But that's being multiplied by RT to the power of C times RT to the power of D times RT to the power of A, divided by RT to the power of A times RT to the power of B. Because the base of all these exponential numbers is the same, namely RT, you can simply bring the exponents together. And the idea is that if you multiply exponents together, you add them. If you divide exponents from each other, you subtract them. So in essence, the RT term becomes the following: Kc times RT to the C plus D minus A plus B, since A times B can add to each other, but they ultimately have to be subtracted altogether from C plus D. So in your textbooks, if you look into it, you'll find out that the expression is given as follows: Kp equals Kc times RT to the delta n. And delta n is simply the difference in the sum of the product coefficients minus the sum of the reactant coefficients. So that's what delta n stands for. And this gives you a really nice way of switching from Kc to Kp. And if you do need to switch from Kp to Kc, in that case you just have to divide Kp by RT to the delta n. Alright, so let's do a quick little example of this. Alright, so in this expression, as you can see, everything is a gas. So we can actually deal with the Kp constant, the Kp expression. And what we're being told right here is that the Kc equilibrium constant for this reaction is 32 at 298 Kelvin. We want to use that information to find out the value of Kp. So the first thing we do is we go and set up the equilibrium constant expression Kc, right? That is actually equal to 32. So you can actually just input that value for Kc. The second thing you need is the temperature, and that's being given here, 298 Kelvin. Now R, because you're dealing with pressure, you got to make sure to use specifically the value of 0.08206 atmosphere liters per mole Kelvin for this to work out. If you input 8.3145, you're going to mess up the entire problem altogether. But look at the value of delta n. That's the sum of the coefficients of the products, which is 2 plus 1, which is 3, minus the sum of the coefficients for the reactants, which in this case is just 2. So you have 3 minus 2, which tells you that, yes, you have 32 times, 0.08206 times 298 raised to the power of 1. And if you carry out the multiplication inside the brackets, you're going to get a value. I would recommend that you don't truncate the number. Keep all the digits that your calculator gives you, then raise it to whatever power coefficient, in this case the power of 1, and then multiply by the outside parentheses to give you the value of the Kp. So the conversion is actually not too bad, but the one thing I want to make sure that you understand is that you will not be dealing with Kp unless everything here, or everything that goes into the equilibrium expression, is a gas. So if you did have solids and liquids, you could still write a Kp expression even if you only have one gas present. But if you do have anything that's AQ, then you probably can only work with Kc, right? So everything needs to be gases, or at least everything that goes into the expression ought to be gases for you to be dealing with Kp's. Alright, so let's stop the video right here. In the next video, we're actually going to do calculations that involve the idea of finding out what happens to the concentrations as they try to reach equilibrium